Today, I introduce you to chapter 6 of physical chemistry, which chapter 6, we are calling it chemical equilibria. We are calling chapter 6 chemical equilibria, the concept of chemical equilibria. Chemical is not a new word to any of us. It's related to chemistry or chemicals. And when you talk of chemicals, we are looking at compounds, basically. Those chemicals are compounds, of course. And then we talk of an equilibrium. We mean that state when the rate of formation of some products in a given reaction is equal to how the products are consumed, the reactants are consumed. So a chemical equilibrium is just that point, any point in time that is reached when the rate of formation of products in a given reaction is equal to the rate of consumption of the reactants. So it shouldn't be something that is confusing, because just like physical changes, we are aware that in physical changes, let me look, for example, at water. We looked at this under the topic phase equilibrium. We say the point is reached when ice is in equilibrium with the liquid water. And when the liquid water is in equilibrium with water vapor. And when the water vapor is also in equilibrium, that can also happen with the ice. When all the three are in equilibrium, then we talk to what we call the triple point. So a state of equilibrium does not stop on these kinds of physical changes. A state of equilibrium can also happen for the cases of can also happen for the cases of compounds. And for the cases of compounds, that equilibrium is what we are calling chemical equilibrium. Are we together, dear friends?
Yes, teacher.
Okay. I may give you a very simple example. When I have magnesium reacting with oxygen, the product formed for this kind of reaction is magnesium oxide. The kind of product is magnesium oxide. Now, that product, magnesium oxide, I think we should balance this equation first of all by putting a 2 there and a 2 here. This reaction proceeds only in one direction. Proceeds only in one direction. The direction that leads to formation of magnesium oxide. Whether you hook or crook, magnesium oxide will never and never form magnesium and oxygen again. So this is a chemical change. It's not a physical change. However, there are some chemical changes where reactants may form products again if the reaction is not done at conditions that ascertain maximum reaction or completion of reaction. For example, if I decompose calcium carbonate, it will give me calcium oxide and carbon dioxide. Calcium carbonate is a salt. Calcium oxide is basic, it is a base. Carbon dioxide is an acidic gas. So during this reaction, there is a tendency of the decomposition of calcium carbonate not to completion, such that the acidic carbon dioxide can react again with the basic calcium oxide to regenerate the calcium carbonate, hence a state of equilibrium between the reactants and the products. It's not only that reaction, there are so many other reactions that do not go to completion and then stop somewhere. The reason is usually because the products that are formed during those reactions do react themselves to regenerate the reactants. Such reactions are called reversible reactions. And in chemical equilibrium, we are going to be dealing with only and only reversible reactions. And in a reversible reaction, my dears, it is always what we call the forward reaction, and a backward reaction. That's why everywhere we shall be using the symbol of that kind. A reaction where we shall always have the forward reaction and the backward reaction. Let me hope that's driven home and understood. What next? Next is characteristics of a chemical equilibrium. What are the characteristics of a chemical equilibrium? One is that it should occur in a closed system. A chemical equilibrium does not occur in the open. And remember, in our phase equilibrium, we find what we call a system. When we say it should occur in a closed system, we do mean that you shouldn't have the reaction in which the chemical equilibrium is involved occurring in the open. Why? There are so many interferences. For example, I've just looked at this reaction. If I allow this reaction to occur in the open, there could be a tendency of the carbon dioxide reacting with the water vapor from the atmosphere. Even the calcium oxide, if the water is high enough in amount, there could be a reaction to form calcium hydroxide or carbonic acid. That's why we need a system that is isolated, where we can have the reactants be put and such the reaction proceeds without interference. That's what we mean by saying that a chemical equilibrium should occur in a closed system. The second characteristic is that the reaction in which it occurs should be reversible. The reaction in which it occurs should be reversible. The other characteristic is that temperature should be constant. Temperature should be constant. it should occur at a constant temperature. We shall later see the effect of temperature on a chemical equilibrium. If the temperature is not maintained constant, temperature is the only factor that affects the chemical equilibrium. And lastly, is that the rate of forward reaction. The rate of forward reaction is equal or should be equal to the rate of backward reaction. Those are the four characteristics of the chemical equilibrium. The rate of forward reaction should be equal to the rate of backward reaction. Are we together?
Yes, teacher.
Yes. Now, those are the four characteristics of any chemical equilibrium. You may make research and find out others. We have said that in a chemical reaction in which a chemical equilibrium is involved, the reaction should be reversible. And at this point, I want us to see the difference between reversible and irreversible reactions. I want us to see the difference between reversible and irreversible reactions. What is a reversible reaction? First of all, talk of a reversible reaction. What comes to your mind? What best comes to your mind? What do you come to understand if somebody talks about a reversible reaction? When you talk of a reversible reaction, we mean a reaction that takes place in both forward and backward directions. A reaction that takes place in both forward and backward directions, such that both the reactants and the products are present in the equilibrium. Such that both products and reactants are present in the equilibrium. Hence, such a reaction does not go to completion. That's what we call a reversible reaction. It takes place both in forward and backward directions. At equilibrium, both reactants and products are present in the equilibrium mixture. Such a reaction does not go to completion. Can we have some examples? Why not? Very many of them. You have looked at a number of reactions that are reversible. For those of you who covered group 7, so that this kind of reaction is a reversible reaction. It rarely goes to completion except under extreme conditions. The reaction between hydrogen gas and iodine gas to form hydrogen iodide. I know I haven't gone very far in terms of organic chemistry, but there is this reaction here, the esterification reaction. The reaction between, for example, ethanoic acid, liquid, and liquid ethanol form ethyl ethanoate. It's called ethyl ethanoate. Two, and then water. All of these are reversible reactions. The other reaction I may think of was looked at in O level, the reaction between iron. I should balance it earlier so that you learn how to balance such an equation. The reaction between iron and water, but the water is in the form of steam. In this case, water is steam. So it gives us tri-iron tetraoxide and hydrogen gas. Can we balance this equation? Yes. By of course having a 3 here to balance the iron and a 4 here to balance the oxygen using this. Then the 8 hydrogens implied should have a 4 here. Usually iron reacts with steam when heated. Because this should be heated. React with the steam, form tri-iron tetraoxide, hydrogen gas. All these are forward reactions. You may think of very many others, but these are the examples I can have for now. I've told you within the whole lesson, we shall be seeing very many reactions that are reversible, because one of the characteristics of a chemical equilibrium is that it should occur in a closed system, and the reaction in which it occurs should be reversible. So that means we are entirely going to be looking at reversible reactions. Hope I can proceed. We can have what we call a reversible reaction, but that does not mean there are no irreversible reactions. They are the most common ones. Those reactions which go to completion. So if I want to define a reversible reaction, what shall I say? If I want to define a reversible reaction, I'll have to modify my definition. Actually, I will just play around with my definition of a reversible reaction. I will say an irreversible reaction is a reaction that takes place in only the forward direction. In only the forward direction. That's the first thing we should note. Such that only products, this time not both reactants and products, such that only the products are formed. And in such a definition, I don't expect you to talk about the word equilibrium, because equilibrium cannot exist if there are no reactants and products at the same time. So we shall say is a reaction that takes place only in the forward reaction, such that only the products are formed or are present at the end of the reaction. And such a reaction can never be at equilibrium. So we are saying it is a reaction that takes place only in the forward direction, such that only the products are present after the reaction. And can never be at equilibrium. Hope I'm a bit clear with such a definition. I've already given you examples of irreversible reactions. I've already given you one example. Let's look at more examples. The first example is the reaction between magnesium and oxygen to form magnesium oxide. That is one of the reactions. The other reaction is that reaction, for example, between ethene and oxygen, for that combustion. Most of the combustion reactions are irreversible. It gives me carbon dioxide gas and the water. The other reaction is reaction between ethyl ethanoate hydrolysis of ethyl ethanoate, alkaline hydrolysis of ethyl ethanoate yields the ester will have to be hydrolyzed to form the alcohol and an ethanoate ion. Such reactions are irreversible. There is no completion and there is no equilibrium in them. All right. If that is understood, let me proceed to what we call a dynamic equilibrium. All these are concepts under chemical equilibrium. There is what we call a dynamic equilibrium. I'll have to look at a case of hydrogen reacting with iodine to form hydrogen iodide in a closed system, which we usually use as a sealed glass tube. Known amounts of hydrogen. You put a known amount of hydrogen and a known amount of iodine. That known amount can be in terms of moles. We are using known amounts so that we are able to see how much of the reactant, so how much of the products have been formed at the end of the reaction and how much are remaining for the reactants at the end of the reaction. If we put the two in a sealed glass tube, when I talk of a sealed glass tube, I'm now bringing in what we call a closed system and heat them to a high temperature. I heat the reactants to a high temperature, which temperature I maintain constant, and leave the glass tube to cool. I give it time to cool. If I analyze the gaseous mixture at the end of the reaction or after some time, I'll find out that in the mixture, I still have hydrogen iodide, I still have some iodine, and I still have hydrogen. That's a key to show that the reaction is reversible or an equilibrium is established. And it implies that still both the forward reaction and backward reactions are still taking place. But what do I want to emphasize? I want to emphasize that due to the presence of both reactants and products at the same time in the reactant mixture, there is an implication that rate of formation of hydrogen iodide would be equal to rate of reaction between hydrogen and iodine. That's one point we should raise. Rate of formation of hydrogen iodide could be equal to the rate of reaction between hydrogen and iodine. It also implies that rate of dissociation, I'm bringing down a new term, rate of dissociation of hydrogen iodide. Dissociation is this backward reaction, hydrogen iodide, to form iodine and hydrogen. Is equal to the rate of reaction between hydrogen and iodine. When that happens, we say that the system is in a dynamic equilibrium. The system is in a dynamic equilibrium. And it brings me to a definition of a dynamic equilibrium. What is a dynamic equilibrium in a chemical equilibrium? A dynamic equilibrium is the equilibrium established when the rate of forward reaction is equal to the rate of backward reaction. Such that the concentration of reactants and products remain constant. That point is reached at a constant temperature when the concentration, actually, I think it would be advisable to add that condition at a constant temperature. When the rate of forward reaction and the rate of backward reaction are equal, such the concentration of reactants and products remain constant. All right. So you read further about the dynamic equilibrium. That's what I have as its definition. Let's proceed to what we call types of chemical equilibria. I'm still introducing you to the topic, and I want us to see the key terms, types of chemical equilibria systems or equilibrium systems. These are two types of equilibrium systems. And the first one is what we call a homogeneous equilibrium system. Homogeneous equilibrium system. And obviously the other one is that one you're thinking of. Which one are you thinking of? Peter, which other system are you thinking of?
Hetero.
The other is the heterogeneous system. Those are the two types of chemical equilibria that we are going to look at. When you talk about homo means similar things, two similar things, or more than two similar things together. Don't confuse it with the homogeneous and heterozygous. Homozygous and heterozygous things in biology, genetics. So on top of the homogeneous equilibrium system, that is one in which both reacts and products are in the same phase. That's a homogeneous equilibrium system. It is a system in which all reactants and products are in the same phase. So if they are all liquids, they are liquids. If they are all solids, they are solids. If they are all gases, they are gases. If they are all in solution, they are in solution. That's what we call a homogeneous equilibrium system. It is a reversible system in which all reactions and products are in the same phase. Let's see examples of such a homogeneous system. I looked at one where I said ethanoic acid is a liquid. When it reacted with ethanol, which is also a liquid, the products are ethyl ethanoate, which is a liquid, and water, also liquid. So liquid, 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 a homogeneous equilibrium system. Both reaction and products are in the same phase. We can look at the reaction between hydrogen and iodine to give us hydrogen iodide. All of them are gases. All the reaction and products are gases. You can look at the dissociation of dinitrogen tetroxide. Dinitrogen tetraoxide is a gas. It decomposes to form nitrogen dioxide, also a gas. That is a homogeneous equilibrium system. How about a heterogeneous one? The heterogeneous equilibrium system is one in which two or more phases are involved. Is one in which two or more phases are involved. Let's look at one. We've already looked at some of them previously. We looked at the reaction between iron, heated iron, and steam to form triiron tetraoxide. Hydrogen is a gas, carbon tetroxide is a solid, water is a gas, in this case, iron is a solid. That is a heterogeneous equilibrium system. We can have the reaction between bismuth trichloride, it's a solution. It's a solution in water. When it undergoes hydrolysis, it forms what we call bismuth oxychloride. This is bismuth oxychloride, a solid, and hydrochloric acid. And hydrochloric acid. So these two here are heterogeneous equilibrium system. Bismuth is a solution. Bismuth trichloride is a solution in water, a liquid. Hydrolysis yields a solid, and then a clear solution of hydrochloric acid. That is bismuth trichloride undergoing hydrolysis. What is the point that I want us to note? Some of you could have not realized this. In chemical equilibria, we are not looking at ions. Most of these reactions do not involve ions. If ions get involved in any equilibrium, then we shall look at that under a reaction, under a topic called ionic equilibria. That's why we have ions in equilibrium, and it will be our next chapter after chemical equilibrium. What have we so far looked at so that you don't forget? I've made an introduction to chemical equilibria. That's one. I've made an introduction to chemical equilibria. I've looked at characteristics of the chemical equilibrium. I've looked at reversible and irreversible reactions. I've also looked at types of chemical equilibria. Types of chemical equilibria. What am I yet to see? I'm yet to see what we call a law of mass action. This is going to be our next subheading.